Again, thank you, Nadine, and I also want to thank KHL, SCNRA, all the sponsors and attendees. Appreciate y'all being here. The project I'm about to show you was a huge success and was truly a green project that included incredible community involvement. This is a segue into our bridge move. Martin, would you please play that short video?
He thought this would be a grand way to celebrate Bruno Nebraska's centennial. Some had no doubt that with a hearty he hoped the barn would go. They just not have to let theirs after that 90 pounds. But others weren't so sure. I hope so. And I think so. To pull off a project like this, you need a lot of muscle, a little help from the rock. It's really fortunate that the total water on how we can work together.
As you can see, the average workforce age there was somewhere around 55 to 60 as well. Actually, Joel Dandria sent me that, suggesting that I open with it. In the spirit of many of our U.S. politicians, I say this: if you enjoyed that little segment, I take full credit. If you didn't, well, blame it on Joel. Really, I'm here to show a job that we're very proud of. It was the Galveston Causeway Bnsf Railroad Bridge span. And our scope of work was to take it from the point that it was erected into full fashion and then transport it about, a kilometer and then roll it onto a 300 by 100 deck barge. That kilometer be all of the metric dimensions that I will mention. And then take that barge and use the barge and the ballasting to position and set the bridge in place. So I ask you to focus your attention on the obstacles we had to clear, above water, below water, and laterally as well. And the clock started on our rigging operations once we positioned the barge in the bridge channel, and we had a maximum of 7 hours to set the bridge, and if we beat that time, we made a bonus. So Martin, if you would start that video there.
Single-link bascule Galveston Causeway Railroad Bridge was known to be the most dangerous bridge on the Intracoastal Waterway. In addition to its narrow 108-foot width, mariners had to negotiate a significant curve in the waterway on either side of the bridge while facing strong south-to-north winds and east-to-west tidal currents in the area. More accidents occurred as a result of collisions with this railroad bridge than any other on the Gulf Coast, costing more than $2 million annually. The U.S. Coast Guard deemed the bridge a navigational hazard and directed the bridge to be replaced. The highway bridge was widened to a 310-foot clearance, and it was deemed the railroad bridge would be widened to the same distance, nearly tripling its overall width. Chinbro and Brassfield and Gorey came together as a joint venture and won the contract for the bridge replacement. Due to the size of the bridge and the location of its final destination, the new single-track vertical lift span bridge was constructed on land at a site approximately 3 miles from the channel. Burkhalter was subcontracted for the transportation of the new lift span bridge to the final bridge site, as well as the removal of the existing bascule bridge. Bridge was 386 feet 8 inches long by 22 feet 9 inches wide and 64 feet 8 inches high. The bridge weighed 3 million pounds. The old Bascule Bridge was 153 feet long, 22 feet 8 inches wide, and 56 feet 6 inches high. The bridge weighed 1,700,000 pounds. Transport new lift span bridge from construction point 3/10 of a mile, roll onto barge, and tow 3 miles to the channel site. Rig and position the new lift span bridge and set on its supports. Rig, lift from its supports, and remove the existing Bascule Bridge. Tow existing Bascule Bridge from channel site 3 miles to the dock, roll off of the barge, and transport to final destination 3/10 of a mile from the dock. Challenges: stability of the new lift span bridge. The vast difference in the height and width of the bridge versus its 23-foot wide depth led to major concerns about its stability during transport. Weight distribution of the Bascule Bridge. By design, the Bascule Bridge's center of gravity was off-center by 45 feet, positioned on one side of the bridge, and creating weight distribution issues on the transporters and the barge. Conditions of the road at construction site. The bridge was constructed approximately 3/10 of a mile from the dock site. As was stipulated in the contract, Burkhalter planned the job with the assumption that a feasible roadway would be available on the construction site to transport the bridge to the barge.
When we showed up and started putting trailers together to get ready for this move, the client was supposed to have provided a road for us from the storage yard across the yard and to load on the dock. But they waited too long to prepare this road, and by now it's been raining for a week or two. The yard is basically a solid mess. So we needed a solution. We had a time constraint. We had a set day that this bridge had to be set. And we didn't need over 500 wheels to get stuck with a 3 million pound bridge on top of it in the middle of the yard and nowhere to go. We decided to make the road with plastic mats. We surveyed the yard, taking measurements, and came up with a plan for the number of mats needed. We soon had mats rolling in by the truckload. We laid the mats out, built the road, and stayed on schedule.
Obstacles on the construction yard. In order to get the bridge from the construction site to the dock, Burkhalter crews had to maneuver the bridge around an existing rail bed as well as a bay inlet. Dock stability. While the dock wall was believed to be plenty stable, a 3 million pound load still brings stability concerns with it. Routing. Due to the enormous loads, the barge size required was too deep for the waterway's main path. The bridge was to be positioned between 2 control towers already in place. Horizontally, there was approximately 2.5 inches of clearance on either side of the bridge. The bridge must come in perfectly aligned, square, and level to fit in place. Additionally, when the new bridge was on its center line, there was only 17 inches between it and the old bridge. If control of the barge was not maintained, the new bridge could easily collide with the old bridge. The impact of the 3 million pound lift span bridge could not only damage both bridges, but would knock the raised Bascule Bridge off its pivot point so that it could not be later lowered for impending rail traffic.
So we have this huge bridge, a railroad bridge. It's almost 400 feet long. It weighs over 3 million pounds, and we have 2.5 inches of clearance on both sides. Quite a tight fit when you consider 400 feet and it's on a barge and it's got 300 feet hanging off the barge. So we had to come in perfectly square and level for it to ever clear. At that point, we had to also be concerned about the existing Bascule Bridge that had been lowered to a 30-degree angle
and then one of the two pinions had to be removed before you could gain clearance for the new bridge. It also put it in a vulnerable position. If we bumped it ever so slightly, it could be disastrous. So we had to be extremely careful to make sure that didn't happen as well.
Gas lines run directly underneath the channel, as do the water lines that supply all of Galveston with water. The barge could not be too deep, or we would hit the lines, not only causing damage to the gas and water lines themselves, but posing safety hazards, environmental threats, and the potential to knock out all of Galveston's water supply. The colossal bridge was 287 feet wider than the barge. While the barge was clearly inside the channel, Burkhalter had to make sure that the bottom of the bridge would not hit the tops of the existing structures, including the dolphins and the rail itself. The goal was to vertically clear the structures, but not by much, since pumping that much water in and out of the barge took a considerable amount of time that we didn't have. The vertical clearance between the bottom of the bridge and the top of the railroad was a meager 9 inches, which brings us to the next challenge. When considering vertical clearances in the intercoastal waterway, a fundamental element to be aware of is the tide level. Burkhalter had to constantly monitor the tide and engineer their rigging process using the tidal charts. The tide directly affected the vertical clearances of existing dolphins and the railway, as well as the barge ballasting requirements to set the new lift span bridge and to lift the existing bascule bridge. Once the new bridge was in place and the process of removing the old bridge began, the tide played a huge factor in the ability to pass underneath the new lift span bridge. Burkhalter had to contend with strong east to west tidal currents in the channel during the positioning and setting of the bridge. Once the bridge was in position, it had to be held there for 3 hours while the bridge was lowered and connected. Weather. During the move, crews faced cold and windy conditions.
So we're in Galveston, Texas in February 2012, and it was Mardi Gras. Most people start thinking about the weather turning nice and having beautiful days. Well, let me tell you, it became an issue. It was cold, cloudy, and very, very windy. And with the wind coming off that water, like with the gale force winds, it actually blew my hard hat off my head into the water one time. Some of my guys joked around, they saw a pelican wearing it later.
We now had a 65-foot tall bridge sitting on a barge in the middle of the channel that had the ability to act as a giant sail. Preparation was key for safety and for the success of the job. A number of additional tie-downs were used to secure the bridge from wind gusts, and the overall precision rigging plan accounted for the wind presence. Time frame. It's already challenging enough to move a 387-foot wide, 68-foot tall bridge, but Burkhalter was working against the clock. There was a set 72-hour marine closure, and within that, 2 12-hour railroad closures. The bridge had to be at the site prior to the first railroad closure, so that the rigging portion of the work could be done within the rail closure, after which previously scheduled rail traffic could then resume.
So in setting this bridge, we were operating under a firm fixed price contract. And in addition to that, there were liquidated damages if we exceeded our allotted time for setting the bridge onto its foundations. Our client had 2 12-hour windows for rail closures with the Bnsf Railroad, and they had severe penalties if they did not meet those times. Of that 12 hours on setting the new bridge, we only had 7 hours to accomplish all our tasks. And then as we removed the old bridge, we only had 5 hours. So it was critical that we meet our time frames because it was going to cost us money per hour if we exceeded those times. In addition, we had a bonus if we beat those times. Our clients' numbers were greater than that, and of course we want to continue to do business with them, so it was of utmost importance to us to make sure that we met those numbers.
The bridges were both transported using a total of 64 lines SPNT, made up of 24 lines of Goldhofer PST and 40 lines of THP that were in 2 16-line 4-file configurations.
The client originally approached us with their plan to use a 250 by 72 barge with a lead-in on the towers to catch the bridge as it came in. And we approached them with an idea to use a 300 by 100 barge because we knew it would offer greater stability and it would allow us to use a rope rail based off of the existing channel so that we could use the barge as a guide instead of the bridge.
Since the initial route was not deep enough to accommodate the 3x1 barge, we mapped out an alternative route through the channel using precise depth analysis. The entire route was GPS mapped with exact data points.
In order to accurately control the bridge and precisely set it in place, we designed a 4-point mooring system. This system consisted of 2 double drum waterfall winches, one placed at the rear and one placed at the front of the barge. The 2 rear lines were used for propulsion and the 2 front lines were used for braking. The 2 rear lines were connected to existing dolphins on either side of the channel, and the 2 front lines were connected to existing structure on the south side. Once these mooring lines were in place, the tugboats went idle and the winches took total control.
Plastic mats were brought in and laid down to cover the muddy yard. Once the road was complete, the transporters were then positioned under the supports the bridge was set upon. The bridge was then secured to the transporters and transported across the yard utilizing 2 separate trailers programmed to operate in unison. Since we were on a limited schedule, Burkhalter took the added precaution to contract for an on-site Goldhofer technical assistant to be available to help resolve any equipment issues which might arise. As a result of Burkhalter's preparation, no mechanical breakdowns occurred and the technician's assistance was not required. Once at the dock, Burkhalter had to deal with a potentially unstable dock wall and the inclined slope to transport the 3 million pound bridge onto the waiting barge.
Anytime you're rolling a load onto a barge, one of the major concerns is where you're going across the threshold from the land onto a barge when it's a floating situation. And we were floating as we went on, so it was a ballasted operation, very slow maneuvers. However, it's always bothersome when you're part of the way on, about the halfway point. Anytime you're doing that, even though you've done your research and the dock wall and where you're placing the forces, or the dock wall is good for that, it's still one of your major concerns. If you put forces on that dock wall that cause it to start fading out into the water. So we had fixed a point there and pulled a tape measure and monitored that very closely to see if there was ever any movement in that. And I'm pleased to report that it never was.
Once the transporters were properly positioned onto the barge, 36 tie-downs were installed to secure the barge and transporter for the barge tow to the installation site. Burkhalter staged the barge the evening before the leave in preparation for the early morning crossing. As a safety measure to compensate for the strong winds, the barge was turned in order to better protect the bridge.
So we set sail that morning and followed our GPS route out to the bridge site. As we got very close, we could hear them talking on the bridge, and we're told later on that they could hear us, but they could not see us. We could see the gunboats that the Coast Guard had out there with M50s mounted on the bow. That was something that I hadn't seen in any of our operations in the past.
As part of the rigging and final placement of the massive bridge on its bearings, it was crucial that the center line of the bridge was precisely positioned on the barge. The placement was based upon field surveys of the barge and the channel center lines. Since the center line of the new bridge was not the same as the center line of the existing channel, Burkhalter was required to come in offset. On February 14th, Burkhalter began lining up the barge for the winch alignment. 20-foot chokers were located at the securement points to expedite the attachment of the mooring lines to the anchors. Making positive attachments to the securement points was critical given the extremely limited time window. The bridge was constantly monitored and trimmed by ballasting to keep it level as it approached. Utilizing the 4-point mooring system, the bridge was minutely controlled and positioned, final to prior set. Once the bridge was in position, 2.9 million gallons of water were used to ballast the barge and lower the bridge onto its supports, utilizing 10 6-inch ballast pumps. During this process, the mooring system was continually adjusted to maintain precise alignment of the bridge. Once the bridge was set, Burkhalter continued the ballasting process to provide clearance under the bridge, at which point the mooring lines were detached and the tugboats moved the barge outside of the channel before the 7-hour time window expired. Removal of the barge allowed the joint venture access to continue their operations in preparing the new bridge for commission and preparing the Basque Bridge for removal. It also allowed the Basque Bridge to be lowered and rail traffic to resume. Within minutes of Burkhalter's timely exit from the channel, scheduled rail traffic was once again crossing the old Basque Bridge. Rail transit had resumed, and the new lift span bridge was in place, but the job was not yet complete. The existing Basque Bridge still had to be removed from the site.
When it came to removing the old bridge, the customer's initial plan was to dismantle it in place, but with tight time constraints and environmental concerns, this didn't seem possible. Another critical issue is that a Basque bridge, by design, the center of gravity is off to one side and not even located over the channel, literally making it impossible to move without repositioning the center of gravity or dismantling it altogether. We proposed several solutions for the customer to remove this bridge. The first of which involved basically cutting it into 2 pieces, leaving the counterweights on shore, and we would take the rest of the bridge out on top of our transporters on the barge. This rose some environmental concerns. We don't know what all paint is on it. We don't know what happens to all the metal that gets cut over an existing waterway. The second option consisted of bringing in extra counterweights and placing them at the toe of the bridge. This would relocate the center of gravity closer to the center of the bridge where we could access it with our transporters on the barge. But the problem is you're increasing the weight of the total bridge, and you've got to source counterweights. And the third and final solution that we actually used was to take existing counterweights out of the Basque Bridge and have them relocated onto the toe of the bridge on a frame that would distribute the load evenly. This relocated the center of gravity approximately 45 feet, allowing us to capture it with our tractors.
The transporters were reconfigured on the barge outside of the channel, and the barge re-entered the channel for the lift of the Basque Bridge. When the second rail closure commenced, we repositioned the barge and reattached the 4-point mooring system following the same procedures utilized during the installation of the new bridge span. Once the barge was positioned under the bridge, the last of the counterweights were relocated under Burkhalter's direction, and Burkhalter began ballasting the barge to lift the 1.7 million pound bridge from its supports. Continual ballasting allowed crews to move the 56-foot tall Basque Bridge underneath the raised lift span to complete its removal from the site. The barge traveled the same route via GPS points back to the dock.
We worked many hours with our client to develop plans that would suit their needs and suit our needs as well. Our engineers and project managers did an exceptional job in executing a great plan. We set the new bridge within the allotted time. We made some bonus. We took the old bridge out in less than the allotted time, and that was good for us and good for our client. We executed a very good plan.
Hey, Delynn, this is Brian Watson. Just calling to congratulate you on a job well done. Very impressive. It did exactly what you said you would do, and I really appreciate it. And on behalf of all of us here at the joint venture, I just want to say thank you.
Yeah, that concludes our presentation. I guess if you have questions, they'll come up later.
Yeah, well, I'm going to ask you a question now, but that's fantastic.
Okay.
Thank you very much. Take a seat. That was
Thank you.
brilliant. Big round of applause, please. Thank you.